So welcome to the lecture on state space method. In this lecture we will discuss about controller design using state space method. So if we recall the design in frequency domain using root locus techniques. So in case of root locus technique, we were trying to change the gain so that the root locus could pass through the dominant poles that will give us the required transient responses. And we use the compensation techniques so that if the root locus is not passing through the dominant poles just by varying the gains, we can put some compensation poles and zeros that can force the root locus to pass through the dominant poles. There we were more focusing on the complex poles, that is the two poles, but for higher poles we had no any control. We were not able to control the system pole that has the higher than 2. So the third pole, if it was very far, it resulted to be very far, then we could approximate the second order assumption. If it is close to the pole, we were expecting that there are some zero that will cancel that pole, and so the effect of higher order pole is reduced. In case of state space method, we get the possibility to control each pole of the system by designing some parameters that can one parameter for each pole. For example, if we have a transfer function GS, so GS could be some numerator and some denominator. So this ds could be a characteristic, it is a characteristic equation that is function of s. So s power n plus a n minus 1 sn minus 1 plus a n minus 2 sn minus 2 plus a1s plus a0, that is, so equal to 0. This will give us the n number of poles of the system. So this is a equivalent transfer function of a feedback system. So it is equivalent closed loop transfer function GS. And so if we take, for example, s square plus a1s plus a0 equal to 0. So if we want to calculate these poles, so s12 equal to so these are the two poles of the system. So we can see that in these poles we have the coefficients of s, coefficient of s power 0, that is constant term, and they govern the value of the poles. So if we want to get these poles to reach some another location some other values. So we have to change this a1 and a0. It means that we have to change these coefficients of these characteristic equations. So if we want to change the n poles of the system or of the characteristic equation, we need n parameters, one parameter to adjust each coefficient. So if we have n parameters for one for each of these, so here if we have two parameters, one can change a1, other can change a0. So we will be able to change these poles so that we can reach to the desired pole location. So in case of root locus techniques or design using root locus, we had this limitation that we were only able to design for two poles, that is complex poles, but for higher poles we were not having any method to design or to place those poles at desired location. In case of state space method, we have this capability that we can put or we can place each pole at the desired location. So we will discuss today, and state space method involves mostly the matrix algebra, and that is supported by several softwares like MATLAB and others. So it is more useful using the softwares, and we will discuss about MATLAB in the last week of this course. So let's talk how to design this controller for the system so that we can keep each pole to the required location. So we have, this is the nth order feedback systems, and there are n coefficients. So a0, a1, a2, an minus 1 and an. So there are n coefficients of this characteristic equation. Now if we want this system to show in state space, so we know that in state space we represent x dot equal to ax plus bu and y equal to cx. Here the d we assume that we are not giving any value to d. So d is 0. We are not giving any feedback to output from the input. So we take this case. So what we do, we have this system. If we represent this system, so we can represent as, here we have b, this is u, there is x dot, there is x, so here we have x dot equal to a into x plus b into u. So this equation and here y equal to c into x. So this output equation. So this is state equation, this is output equation. Now in order to design the controller so that it can place, it can control each of these coefficients. So what we do, we give this state variable as a feedback to the input. So we give this as a feedback to the input. So here what we do, we have here this u, b, now we are going to give this state to here as an input with some parameters, gain parameters k minus k. So we are going to give this so now what will happen, that we are giving these parameters, these k's, these values of k we can adjust. So we give this as input so that it will change these values of these coefficients, and we can see how. So now the state equation will be changed. So what will be the state equation? We can see x dot here will be ax plus, now b, and here is u plus minus kx. So we can write minus kx. So this we can write a minus b k. So a minus b k x plus b u. So here this matrix, now A is A minus BK, and with changing the K we can change this matrix. Now Y equal to Cx. So now this system we can represent in state space form. So we can write this A as 0, 1, 0, 0, then 0, 0, 1, 0, and so we can write this last row will collect these coefficients in negative and reverse order. So minus a0 will be here, then minus a1, then here minus a n minus 2 and minus a n minus 1. So these terms will be here. So this is matrix A. So we can directly, I have written directly because we already know how to write a transfer function to state space matrix. Now the matrix B. So B, we know that we have only this input U. So we write B zero, 0, here 1. So into U. So we have an input here. Now matrix C, so we assume that matrix C is, their elements are C1, C2 and Cn. Now we assume that we have matrix K. So K is having this K1, K2, Kn. So n parameters that can help to adjust this. So now here, if we could, now for this system, the matrix A minus Bk. So matrix A minus Bk we can write, if we want to write matrix A minus Bk. So A minus Bk is, we have this matrix, so there will be no any effect. So B into K we will calculate first, matrix B into K. So we know that this is n into 1 and this is 1 into n. So we will get a n into n matrix, and then we compute A minus Bk. So this matrix minus this matrix. So what will happen? We will have the coefficients K1, K2, Kn, they will be minus here. So here A minus Bk, this matrix we can write so 0, 1, 0, 0, then 0, 0, 1. The last row will be minus A0 minus K1. So minus A0 plus K1. Then second term will be minus A0 plus K2. Minus A1 plus K2, sorry, here it is A1, the second term. And then the last term will be minus A n minus 1 plus K n. So this is the matrix. So this is equation 1, and now from this matrix we can write the characteristic equation, that is s power n plus, now a n minus 1 is a n minus 1 plus k n, s n minus 1 plus a n minus 2 plus k n minus 1, Sn minus 2 plus A1 plus K2 S plus A0 plus K1, that is equal to 0. This is equation number 2. So this is the new characteristic equation when we have these parameters k. So we can rewrite this equation as Sn plus d dn minus 1 Sn minus 1 plus dn minus 2 Sn minus 2 plus d n d1 s plus d0, that is equal to 0, where di equal to a I plus k I plus 1 for I equal to 0 to n minus 1. And so here k I plus 1 equal to di minus ai. So we have found this equation. So now we have n values of k, and each k can change these coefficients, these earlier coefficient. So we can select the values of k such that these coefficients will be changed and each pole can be placed at the desired location. So we will take one example and we can discuss about this application. So let's take one example. So before that, so here we follow this. So design via state space, we understand the differences between root locus technique and state space method. So here after designing the location of the dominant second order pair of poles, we stop hoping that the higher order poles do not affect the approximation. The root locus technique does not allow for a sufficient number of unknown parameters to place all the closed loop poles uniquely. One gain to adjust or compensator pole and 0 to select doesn't yield a sufficient number of parameters to place all the second order poles at desired locations. So to place n unknown quantities, we need n adjustable parameters. So we have found the n adjustable parameters using the state space. But here we see that the state space method doesn't allow the specification of closed loop 0 locations. So here we cannot put the zeros, but we are able to put only the poles. So we have found these values. Now we come to this numerical example. So here the numerical example is that a plant is given, that is gs equal to, so we are given gs equal to 20s plus 5 upon s plus 1 s plus 4. Now we have to design the phase variable feedback gains so that to yield a 9.5% overshoot. Design so that we get 9.5% overshoot and a settling time equal to 0.74 seconds. So we get a settling time Ts 0.74 second. So we have to find those gains k, value of k, so that we can. So now here we know that here we have the system like gs, rs, cs. So we are given here the gs, and what is the characteristic equation? So we can see here we have this, we can write this equal to 20s plus 100 upon, so we solve this s plus 1 s plus 4, so we will find s cube plus so we find this equation. So this is the characteristic equation, and from on this problem we will apply the theory that we developed in this lecture, and we will continue this problem in the next lecture. So see you in the next lecture. Thank you.